Welcome to Atoms to X-rays, a series about new developments in the physical sciences. Atoms to X-rays is brought to you by the Division of Physical Sciences and the San Diego Foundation's Reuben H. Fleet Foundation Fund, sponsors of the Atoms to X-ray website for teachers and students. Please visit the site and let us know what you think. We hope you enjoy the program. It's my pleasure today to introduce my colleague from the Department of Physics, Professor Frances Hellman. Professor, as I say, is a physicist. He did her bachelor's degree at Dartmouth, PhD at Stanford, and she works in a very interesting area that I'm actually looking very forward to hearing about it. All of us know from information storage and processing that you have materials that are really important for doing this. In one case, silicon, and in another case, magnetic materials, largely metallic, and in one case they deal with spin, in another case with charge and magnetics. And what you're going to hear about today is what's out on the frontier of these new materials, how they're made, how they're used, what their advantages are, and it's an area called spin electronics. Thank you, Frances.
Well, thank you very much for inviting me to give this talk. I'm really looking forward to explaining some of the research that I do and hopefully convey to you why I think it's exciting and what its potential are, what its challenges are, et cetera. So I'm going to be talking about spin electronics, and I hope that I can convey to you both why it is interesting and scientifically interesting, but also why it is technologically important, both for current technology and as a potential future technology. In order to do that, I'm going to start by telling you a little bit about magnetism and what makes materials be magnetic, and semiconductors and what makes materials be semiconductors. And then I'm going to turn to the topic of how do we combine them. How do we make a magnetic semiconductor? Why would we want to make a magnetic semiconductor? What are the potentials? Before I proceed any further, however, one of the important things to point out is that science is just simply not done in the vacuum that many people think of it. It's not a solitary occupation, and the work I'm going to describe, both work already done and work we're proposing to do in the future, I have had many collaborators and hope to continue with that. And I've listed some here, ranging from fellow professors here at the university and outside, a number of graduate students who've been directly involved with this project, undergraduates. I've had quite a few undergraduates in my group involved in various aspects, and one has to always be sure to thank the sponsors of this work, which have been both NSF and the DOE. So let me start by pointing out, this is actually an image I got from the IBM website of an IBM ThinkPad, and a typical computer consists of course, many components, but two of the key components are the CPU, the processor, and I'm going to lump into that also some specific parts of memory, the random access memory and the cache memory, which are currently volatile, meaning when I say volatile, what I mean is that if the power goes out, they lose whatever it was they were doing, and you have to reboot. By contrast, of course, one of the other key components is the hard drive, and the hard drive is where we store information. The CPU consists of millions of transistors. I've shown here just the Pentium, but inside here are millions, literally, of transistors. And here is a schematic, which I'll come back to later and describe what it is and what I'm showing you. But this is a schematic of a single transistor. And the key point of this is it is based on silicon. Okay? The entire processing portion of your computer and of all processors are based on silicon. There's some efforts to go into things like gallium arsenide, but silicon is really the name of the game. The hard drive, shown again up here, on the other hand, is based on magnetic materials, which are basically either cobalt or iron in the context of a hard drive. And I show here a schematic of what goes on inside here. This area down here at the bottom is the disk, is the actual magnetic material, and in that disk are bits, the zeros and ones that you always think of, when you think of computers. Those bits consist of little bar magnets, little north and south regions of the magnetic material pointing one way or the other way. And so those are norths and souths. We have a right head, and that right head makes these bits one way or the other way by producing a magnetic field. We also have a reed head, and I'm going to come back later in the talk to the reed head, and I'll define what this means, this MR or GMR sensor. But the reed head is a separate unit, and it detects the magnetic fields of these bits. And so that's how we read and write the zeros and ones. And this is a permanent storage system. When you turn the power off of your computer, it's, of course, still there. That's the whole point of storing things. Now, in order to describe any of this, I have to turn to the periodic table. I'm really a materials physicist, which means that this periodic table is really my, if I were an artist, this is my palette. This is the starting point. And so, looking at this periodic table, here are the semiconductors that we primarily use, silicon and germanium. And you'll notice that there's only two of them. I mentioned briefly gallium arsenide, which is right there, which has some advantages over silicon and germanium, but I'm not going to talk about those today. But silicon and germanium are the main semiconductors that we're interested in. Here are the magnetic ones: iron, cobalt, nickel. And then there's another group down here at the bottom of the periodic table. This stuff that's stuck down here on the edge, it's put down there because it really belongs right there after lanthanum. It's elements 58 through 71, I think it is. And they're put down here. They're called rare earths or lanthanides. And they're all magnetic. So those are the magnetic elements in this table. And I just show there a little picture of something that's magnetic so that we're all clear what I mean. Now, what makes something be magnetic? Well, in order to understand that, I have to go right back to the beginning. An electron has a negative charge, and of course it also has a mass, positive mass, but also has a mass. And a moving charge is what we mean by an electrical current, and that's what makes light bulbs light, etc. In addition to the charge, they have a spin. And now a spin you can think of in a classical way, just like the spin of the Earth. Think of this electron as just spinning around its own axis like that. And when I draw the arrow pointing up like that, it means it's spinning one way. If the arrow is pointing down, it means it's spinning the other way. Okay? Now, that spinning electron produces magnetic field, and these are the magnetic field lines that I draw associated with that, and I call that thing a magnetic moment. Now, the interesting part about that is the exact same pattern that I get if I consider a bar magnet with its north and south poles. I get the same pattern of field lines, and in fact, what makes up this bar magnet is a whole bunch of those. Okay, all lined up parallel to each other. So just, many, 10 to the 23rd per cubic centimeter, roughly, of little arrows like that make up this bar magnet. But it's the same pattern. Also, interestingly and importantly, if I make a current-carrying loop, I take a piece of wire and make it carry a current around in that direction, it produces also the same pattern. So this characteristic magnetic field line is seen everywhere. And the bottom line is that magnetic moments, or really any moving charge, produce a magnetic field. Okay, now, that is a single electron. And what happens now, electrons don't usually exist all by themselves. So now, getting back to the periodic table, this is what's called an electron shell structure of the hydrogen atom. Hydrogen is the world's simplest atom. It's the first element on the periodic table. It therefore has one proton and one electron in its most common state. And so that one electron has a spin. The proton also has a spin, but it's very small, and it's not something that we're going to worry about for today. So that's what happens to the first element. There is the 13th element in the periodic table is aluminum, something you're all very familiar with. It's a shiny metal. Aluminum has 13 protons, 13 electrons, and they're arranged in a very characteristic and very important way. There's 2 electrons in this inner shell. There are 8 electrons in this second shell, and this third shell is only partly filled. And that partial filling is absolutely crucial. In fact, in general, we will not bother showing these inner shells. The inner shells we will just lump together with the nucleus and show it as just what we call the core. So we have the core of the atom, which has the nucleus and those filled inner shells, and then the only ones that we're really going to continue to keep track of is this unfilled outer shell, which has 3 electrons in it. Now those outer 3 electrons, you'll notice because it's an odd number, there's 2 up and 1 down. And that leads to a really important point. An isolated aluminum atom is magnetic. It has 1 extra up spin. Okay? Now, for the experts in the audience, I'm glossing over some rather significant details here having to do with orbital motion versus spin motion and things like that, but for the purposes of illustration, you can think of it as being as simple as I'm describing. So the isolated aluminum atom is magnetic. At this point, you should stop and say, wait a minute, aluminum is like what lots of things are made out of, and it's not magnetic. And hopefully everybody doesn't think of aluminum as magnetic, and they would be right. Aluminum as a solid is not magnetic, but an aluminum atom is. So what happens? What happens is when I make a solid piece of aluminum, here are the cores all stuck together like that, and in fact they do pack rather closely into a crystal structure. So you can think if I brought some, this is not the correct crystal structure for aluminum, but it is the correct crystal structure for some other materials. You can think of these as being the cores, and so they all stick together closely. And what happens is that includes those inner shells, but those outer shells, those 3 outer electrons, detach themselves from the core. The technical word for that is they delocalize, and they can move. So those 3 outermost electrons are just shown as they no longer are attached to an individual atom. They are actually shared by all of the atoms. So each one of these electrons is actually, you can just think of it as being shared by all of the atoms, and that's what we mean by a metal. So for a metal, these electrons just exist in a big sea, and they can move around. Okay? The crucial part, the first crucial part is it's a metal, which means if I take a battery and a light bulb, and I put a piece of aluminum in the middle of this rather elementary circuit, and I look at the electrons in there, they move, and the light bulb turns on. Okay, so these electrons are able to move themselves around the circuit and turn the light bulb on. That's what I mean by a metal. Okay? Now, the crucial part, however, is now, even though there was an imbalance with the isolated atom, there is now, once they distribute themselves over the whole metal, there is, for quantum mechanical reasons, they want to go in states where there's as many up as down. And so the end result is there's as many up as down of these electrons in here, so it's not magnetic. So aluminum is, although as an isolated atom it's magnetic, it is not magnetic as a solid. Okay, so that was aluminum. Aluminum is element 13. Let's turn to silicon. Silicon just has 1 more electron, seemingly a rather small difference. I go from 13 to 14. Completely alters it. Silicon is not a metal. So here I'm showing only the core. I'm going to ignore that first and second shells, which are full. It has 1 more electron, so instead of having 3, it now has 4 electrons in that third shell. Those 4 electrons, I've shown them the way they are for the isolated atom. There's actually 3 up and 1 down as an isolated atom for reasons that I'm not going to go into today, but they arrange like that. So the end result is the silicon atom is also magnetic, but those 4 electrons, because of details of the states they're in, want to go into a shared state, what we call a covalent bond, with their neighbors. So the silicon structure, which is shown schematically here, each silicon atom wants to have 4 neighbors and share each of those electrons with one of those neighbors. So in fact, it makes this rather beautiful shape of a tetrahedron. So it's a little hard to see here. I'll show you more pictures of it. But it makes a shape where each silicon atom has 4 neighbors arranged in this little tetrahedral shape, okay, which is shown here. That is actually the structure for both carbon or silicon. So in other words, diamond also has that same structure. The diamond that you're all familiar with in rings has exactly the same tetrahedral bonding. There's a picture of the silicon structure. Again, so there you can see there's 1 central atom, and then it has its 4 neighbors. This is a 2-dimensional representation of that structure so that you can see it more easily. The numbers here, which I will just show one time, those numbers reflect a displacement into or out of the page so that I can represent this structure in a flat image. The thing that's nice about this is you can now easily see, take this central one, that it has 4 neighbors, and each of its electrons, so it had 1, 2, 3, 4, and it picks up 1 from each of the neighbors, and so you end up with this paired structure like I'm showing. That's what we mean by a covalent bond. And the important thing for the purpose of this talk is these electrons are all paired, so it's again not magnetic. And in fact, it is a very generic statement that when I start making solid materials, those outermost electrons, the ones that make the isolated atoms be magnetic, are exactly the same electrons as produce the bonding in the solids, and therefore they always end up in these paired states. So there, in fact, the question I will come to in a minute is why, therefore, is anything magnetic, which should be the next thought you have. It sounds like they will end up with nothing ever being magnetic. The other crucial part of this is these electrons are attached to the core in what we call a covalent bond, and they can't move. And so silicon is insulating, meaning if I put it in this same simple circuit with a battery and a light bulb, the light bulb doesn't turn on because the electrons are stuck here and they're not free to move around. So the electrons are stuck, the light does not turn on, it's not a metal. So how does anything ever end up magnetic? Well, let's talk about iron. Iron is the first thing in the periodic table that really does end up magnetic. It has a filled first and second shell, but, and this is the important point, it has partially filled third and fourth shells. Now, the reason that happens is a detail of the energetics of putting these electrons in, but the result is it has partially third and a partially filled fourth shell. So now, when I make it into a solid, the fourth shell, those outer ones, those two, delocalize, become detached from the core, and make iron be a metal, which it is. But the third shell electrons stay stuck. Now that's again, that's an oversimplification of what is actually a rather complex problem. But it's a pretty good picture to simply think of those third shell electrons as remaining part of the core. There's an imbalanced number of them. There's 1, 2, 3, 4, 5 up and only 1 down. So I have a net of 4 electrons with spin up, and so I end up with this large core spin. Okay? And that, in turn, that large spin, not just one electron now, but the entire, think of the entire atom now as being a magnet, even though it's in a solid structure, produces the magnetic field lines I showed you before and makes iron be therefore magnetic and have all the properties we associate with magnets. Okay. Reminding you of the periodic table again, that's a pretty good description of iron, cobalt, and nickel. Let me now turn to the rare earths. Not pretty much the same story. Here, there's yet more electrons, and so it's now not just the third and fourth shells, but the fourth, fifth, and sixth shells that are involved. As a solid, 3 electrons. The sixth shell has 2. The fifth shell has just 1 in an unfilled state. Those delocalize, i.e. they become detached from the core and they make gadolinium be metallic. But these 7 electrons that I've shown here in the fourth shell stay attached to the core. And that, I now have 7 all pointing up. And that gives me an enormous magnetic moment. So 2 things about gadolinium compared to iron. One, the core is really big because I'm way out now into 4th, 5th, and 6th shells. So I have all these cores. And so the result is it's very large. 2, I have a very big magnetic moment. Okay? Now, turning back to the periodic table, the world's most powerful magnets right now are actually a combination of what are called, they're called rare earth magnets. If you look them up in sort of science catalogs and things, they're called rare earth magnets, and there's 2 that are made. One of them is a mixture of samarium and cobalt, and one of them is a mixture of neodymium and iron. Okay? But they're basically a mixture of one of these and one of these. And there's reasons for doing that, but the result is I'm showing here one of these really powerful magnets, and you can see the forces are strong enough that it easily holds through my hand. And in fact, I can let's flip it this way. I can flip one over by simply flipping the one. These are strong enough to exert a substantial force right through my hand. Okay, my hand is not particularly magnetic, so the magnetic field lines just go right through. Okay, so I hope everybody can see that fairly easily, that I'm able to just turn this over, but it's quite an appreciable force there. And these are actually the neodymium iron magnets, which are really the strongest. Okay, so now, this talk is partially about magnetism, partially about semiconductors, so let me turn to the semiconductor side. What is so special about semiconductors, and silicon in particular? Well, the thing that makes semiconductors so special is, let me try adding a little bit of aluminum to silicon, and I mean a little bit, like a part in 50,000 is a good typical number. Aluminum, remember, has 1 electron less. It was 13 and silicon was 14, so there's 1 electron less. So there is shown grossly overrepresented as to how many I have, but there's 1 aluminum atom. It likes to sit in the same places that silicon sits, but it's missing an electron. So you can look at that missing electron like a bubble. Okay? And in fact, those missing electrons move around like bubbles in a glass of water. They act as though they were positively charged carriers. They're just missing negatively charged carriers. And so they move around very much like a bubble. You'll notice, if you were paying really close attention before, that this is moving in the opposite direction through this circuit, and that's because it's a positive charge instead of a negative charge. But the result is that the light turns on. So silicon doped, which just means with a little bit of aluminum introduced, acts like sort of a metal. Only semiconductors are so sensitive to these tiny changes. This is a part in 50,000. If I put a part in 50,000 of aluminum into copper, nothing would happen. It would make no difference. If I put a part in 50,000 of aluminum into silicon oxide, window glass, nothing would happen. It's only semiconductors that have this incredible sensitivity to small changes. And that's really the heart of why they are so important and why they're so valuable, is because little tiny changes result in big, small changes result in big effects. Okay? But you'll notice it's still not magnetic. I still have just as many ups as downs. So I can do some interesting things with this. But the thing I can do with this is make a transistor. So if I add a little bit of aluminum, aluminum had one less electron, so it makes p-type or positively doped silicon. If instead I add boron, which is element 15, it has one extra electron, that makes n-type or negatively doped silicon. And that allows us to make a transistor, which is the thing I showed you at the beginning, which is a switch. This is the heart of a computer. It's the zeros and ones that make up all processing and all memory. So this is a structure that I build out of silicon in order to make a transistor. It's got p-type silicon down here. It's got these regions of n-type silicon separated from each other. There's a crucial little gap right there, which is the p-type silicon. And then I have this thing I call a gate up on the top, which is a metal. This is the source of electrons. This will be the drain, or the place that the electrons go. And so what happens here is if I apply a voltage, which I'm going to show as a great big green arrow, I apply a voltage right here to the drain, and nothing happens. Electrons would like to get dragged from the source over to the drain towards this positive voltage, but they can't because there's this gap in the middle. And that's what we call a zero. That's the zero state. If I now apply a voltage to the gate, what it does is it sucks electrons up from this p-type silicon, makes something that we call a channel here, and now electrons can flow. And that's what we call a 1. So the gate is the thing that controls the flow of electrons from the source to the drain. Now, the topic of our research. Can we make a magnetic semiconductor? First question you should ask is, why would we want to? What is the point of making a magnetic semiconductor? So let me give you a few reasons. First, I will start from the most practical. There are potentially large and useful effects. And so let me go back to the structure I showed you at the beginning. This is the hard disk. There's this thing I called a read head, and I put this thing I told you I'd come back to, MR or GMR sensor. That is what reads the magnetization of these bits. This read head is based on a technology involving magnetic metallic layers with something called GMR, which stands for giant magnetoresistance. They detect magnetic domains, the zeros and ones, whether this is north or south, which way around it is, on the hard drive by measuring a change in resistance which is induced by the magnetic field that these each produce. Okay? That not only is a current technology, that's a technology that was developed in a research laboratory, actually a physics research laboratory, only about 15 years ago, and is now in every hard drive that is being sold. Virtually every hard drive now contains this GMR read head. Despite the name, giant magnetoresistance, the effect is actually rather small. Present read heads, it's about 16% at room temperature, 16% change in resistance on applying a field, and that's fairly small, which limits the sensitivity, limits the bit density, things like that. If we could make a magnetic semiconductor, it is likely that the effects would be large. Now, why do I say it's likely? Because semiconductors are really sensitive, as opposed to metals. This present GMR head is based on metals, and effects there just are not as big. They're not as sensitive to small changes as semiconductors are. So that's a rather qualitative statement. I can back that up with some data that I'm going to show you in a couple of slides. That was a very practical reason, a rather short-term goal. The longer-term goal, and I am a physicist, I'm really not an engineer, which means, what I work on usually has longer range implications than developing a better read head. I'm hoping to find things that engineers could then turn into practical things somewhere down the line. So the things that particularly interest me is the fundamental science of the interactions between the moments and the electrons. What happens as the electrons of the metal move past these magnetic moments, and how do they interact? There's some very important fundamental science involved in that. The next statement is almost just an aesthetic one. The electrons in semiconductors have spin, and we're not using it. Okay? We make a transistor. It is entirely based on the charge of the electron, but it has a spin, and we don't take any advantage of it. So there's just an aesthetic thing there that we could probably make something better if we took advantage of all the properties. The final statement is, could we think of combining the processing and the memory functions? Now, a very practical thing is, could we combine the CPU and the hard drive? Now, there may be good reasons we don't wish to combine the CPU and the hard drive. There's a good reason to have a separate unit. But what I will suggest to you at the very end of the talk is that it might revolutionize how we even think about computers if we combine the memory function with the processing function. Just to make you think a little bit about it, your brain, it's not so separate. In your brain, memories and thinking and thoughts are much more tied together than they are in computers. It's not this, there isn't this separate, like there's a processor and then there's a memory. They're much more integrated. And so if we could do a better job of integrating this, obviously it would be faster. Clearly it would be faster. If we didn't have to go back and forth between memory and processor all the time, the computer would run faster. But it's worth thinking about that maybe there'd be a more profound change than just a faster computer. So how do we make a magnetic semiconductor? Well, let's go back and look at the periodic table again. Here's the semiconductors. Here's the magnets. They don't look very far apart. It looks like I could just mix them together. But part of the stuff that I didn't tell you about that shell structure is it was very, very oversimplified. The third shell, iron is an unfilled third shell, so is silicon. But they're very different parts of that third shell, okay, aspects that we're not going to get into. So it is not as simple as let's just mix them together. In fact, one of the interesting points here is out of all of these elements, there are seen when you first look at the periodic table, like there's an infinite variety. But there really isn't. There aren't that many choices. There really are only a few magnets and really even fewer semiconductors. So you have a fairly limited palette to start with when you start trying to create new things. So the first try, let's just try and put some magnetic atoms into silicon. The problem is they don't fit. They have the wrong electron structure. They're just, the structures are incompatible. It's kind of obvious with gadolinium, which is one of those rare earths, because gadolinium, the core is really big, and it just doesn't fit in here. But in general, even iron, which is closer to the same size, the technical term is solubility. The solubility of iron is just incredibly small in silicon. It just doesn't, it's the wrong structure. So you can't do that. So one solution to that is something we've been working on now for many years. I can make the silicon what we call amorphous, which basically means non-crystalline. So here's the silicon structure again, but just a little distorted. Okay, on average, each one of these still has four neighbors, but every now and then there's one that only has 3, and there's some in other parts that might have 5. So it's just a little bit distorted. In fact, this is an exaggeration of how distorted it really is, so that I could just fit it in such a small space. If you looked locally, you would mostly see silicon with a same tetrahedral bonding, but just a little bit distorted. That little bit of distortion allows me to accommodate bigger atoms and different electron structures. The whole thing's not as rigid. So I can put, for example, gadolinium in. Okay? And this is something we've now been working on for quite a while. So I want to emphasize this all is starting to sound rather like a physics lecture, but in fact, there's research here. This is I'm an experimentalist. I work in a laboratory, and in particular, I have my various students and postdocs, many of whom are in the audience today. And this is a picture of a couple of people in my laboratory making some samples. This is a vacuum deposition system, so here they are preparing samples, and somebody measuring some samples. So I just wanted to kind of point out this isn't all just an abstract concept. So the result of putting these gadoliniums in here is that the electrons, those extra outer shell electrons, are able to move around, and they do carry a current. like aluminum. It does act like a metal. But now the conductivity depends strongly on magnetic field, which is what I call magnetoresistance. And that's basically because there's an interaction between these delocalized, these metallic electrons with their spins, and the localized core spins. Okay? It depends on their relative angles. It's like they want to be a particular orientation. And so what happens is, if I have zero magnetic field, these gadolinium core spins are all misaligned. They're all over the place. And the result is when the electrons try and move through here, they do so, but with difficulty. It's as though all those randomly aligned cores got in the way. Okay, so the light, to capture this idea, what I said is the light turns on, but weakly. And so now when I apply a high magnetic field, I line up those gadolinium cores, and now the electrons move much more easily. And so I've captured this in the idea that now the light turns on more strongly. Okay, so the electrons can move much more easily when all of those core spins are all lined up with each other. Now again, I am an experimentalist, and I don't want you, in a technical talk, this would be filled with plots like this. I feel obliged to show one plot of data and not just entirely pretty pictures, because research is actually about data and experiments and things like that, and not just drawing. You can't just sit there drawing pictures of gadolinium cores and things. So this is a plot of some data we've taken. This is the electrical conductivity, which is just how easy it is for the electrons to move around, versus temperature at different magnetic fields. So let me just focus on two of these. That is, the electrical conductivity is a function of temperature in zero magnetic field, and that is the same thing in a high magnetic field. The change, right from there to there, is 5 orders of magnitude, a factor of 100,000. Now you remember when I first showed you GMR, I gave you this term, MR, magnetoresistance. GMR is about 16%, okay, 0.16. This is a change of 100,000. All right? It is an enormous, enormous effect compared to the GMR that is currently in the read heads of computers. Okay? So this sounds fantastic. This is exactly what I was saying. Semiconductors are incredibly sensitive. So by putting gadolinium into silicon, I've made this unbelievably sensitive read head. There's just one tiny little detail, which is that temperature is 1 Kelvin. All right? 1 degree above absolute zero. Now, if we were willing to have our computers function at 1 Kelvin, we could even have them function at 4 Kelvin. We could even have them perhaps 77 Kelvin, which is liquid nitrogen temperatures. That's up at about here. We still have a fairly large effect at 77 Kelvin. We would have a much better read head than what's currently made. But we don't. I mean, nobody really wants to operate their computers at 1 Kelvin. It's also very high magnetic fields, which is a second and at least as significant a problem as the low temperatures. So the bottom line is this material that we've been working on is really not of interest, at least in its present configuration, as a replacement for a read head in a computer. It's really the fundamental science that's important. Okay. Now, that was work we've been doing. Let me turn now to proposed work. And this is work we're just beginning. We're hoping to get funding for. There's people all over this campus that I'm working with. We're applying for grants, and we'll hope it happens. The next effort is, instead of trying to mix it, let's put the magnetic material on top of the silicon. And so then the idea is I'm going to try and inject spin polarized electrons, means spin up electrons, into the silicon by applying a voltage. So the iron, I'm just showing iron now, I'm not going to do gadolinium. So the iron on top of the silicon, and I'm showing it magnetized to the left. And when it's magnetized to the left, and now I apply a voltage, and I have to note that that's a minus voltage because I'm going to push electrons away here, not draw them in. What happens is I push electrons down into the material, and when the iron is magnetized to the left, a high percentage, not 100%, but a high percentage of those injected electrons are also to the left. Okay. So when I take this layer and put it into the same circuit I've been showing you all along, and I apply a voltage just like that, what will happen is I should get spin polarized electrons moving through the circuit. Okay? So there is my spin up electron moving through. Now, there's really no value at all, at least that I can think of, to having spin-polarized electrons traveling through light bulbs. So that's not really the goal of making this kind of structure. The real goal for the first stage of this research is very fundamental science. It's understanding what percentage of the spins are polarized when they get injected, what happens, they can get scattered. What happens, does the spin stay up or does it scatter over into a spin down state? What's the effect of having a thin oxide layer in between them? What happens if instead of using iron, we use iron silicide, which is a mixture of the two, which is likely to be the actual thing that happens at the interface. But we think we can take advantage of that instead of having it be a liability. And so there's lots of very, very fundamental questions, which is the first stage of this research, is just understanding what happens when we try and drive spin-polarized currents into silicon. Now, I mentioned what we call the spin-flip scattering length. Even if the electrons start off being up, they will eventually get flipped to being down. And that length scale that they get flipped on is short, relatively short. And so one of the interesting things about this is you've probably all heard the term nanostructures, nanoscale, nanoscience. Because of this reasonably short length scale, we do need nanostructured devices in order to see the effects that we're hoping to see. So I took a view graph from Ivan Schuler's lab, one of my collaborators in this project, and this is a scanning electron micrograph of a structure he's made. Shows these patterns are all made out of iron on top of silicon. This right-hand picture is just a magnification of that little structure right there. So each of those is that. And what the crucial point here is that little teeny gap right there, just that tiny, tiny little gap. Okay, that is iron, and in between is silicon. And can we get a spin-polarized electron from there to there? Okay, and what there is here is different distances between the iron and the bottom iron. So different amounts of silicon that it has to get through. And the question is, can these spin-polarized electrons make it across or not? The next, and the real goal of this proposed work is to try and build something called a spin transistor. So the idea of the spin transistor is very much like the original transistor that I showed you, except for instead of that N-type silicon, we're going to have a magnetic layer here, probably Fe3Si, for both source and drain. And I don't think the metal gate, at least in the current plan, is just going to stay as some metal. We haven't thought of a reason that would matter if it was magnetic. So we make these layers be magnetic. So the first step is there's the magnetic moment of one layer. And now the crucial thing, I'm going to start by having the magnetic moment of the drain be in the opposite direction to the source. The source and drain are oppositely magnetized. With it arranged like that, I apply a voltage here just like before, and nothing happens. But nothing happened before either, so that's not really the interesting part. The interesting part is apply a voltage to the gate. What happens now before, when they were not magnetic, is now the electrons flowed. However, electrons from here are polarized one way, and they will have trouble getting into this region here because it's polarized the opposite direction. So in an ideal spin transistor, even when I apply both of those voltages, no electrons would flow. A real spin transistor will not be as off as that. It's likely that there will be a small number, but not zero. And actually, that will lead to some interesting possibilities. It may be not only a reality that some will flow, it may actually be useful that some will flow, but not as many. Then what I do is I bring a magnet in, which applies a magnetic field to the drain in the opposite direction to the way it's magnetized. It flips the magnetization of that layer. Now they're magnetized the same way, and now spin-polarized electrons can flow. Okay? And so the idea is the electrons really only flow when the gate is on and the magnetic layers are aligned. And so that gives me an additional control of the transistor, more control of these zeros and ones through use of a magnetic field. Okay. What's the point of the spin transistor? And now I'm going to start getting fairly speculative. So in increasing order of speculation, first of all, additional control of transistor. Okay, I can control the zeros and ones with a magnetic field. That may be useful. Two, I can start thinking about integrating logic and memory because those magnetic layers stay. And so the whole idea is that there's a memory built into which way they are magnetized. So I can have a a memory as a component of a transistor, as an integral component of a transistor. It's possible I could think about some kind of field programmable logic, because I can, field meaning not, well, double meaning to the word field, magnetic field, but also out in the field. So even once the thing shipped, I could think of being able to control what my zeros and ones were by bringing magnets in controlled ways. I could switch what the meaning of a 0 and 1 was. Non-volatile functioning. This logic is at least partially automatically stored halfway through, even if the power goes off, because of the nature of the magnetism. It doesn't go away just because the power is gone. Instead of just zeros and ones, perhaps I can get into higher order logic. Right, now this comes back to, I have a more complicated switch. I have something that is more advanced than just a 0 and a 1, so I can turn that into a higher order logic, not simply binary logic. Okay? I could possibly take advantage of what I call the real spin transistor properties, where I had a little bit of current flowing, but also there's just a more sophisticated logic option here. And now is where we get truly speculative. If I can think of combining logic and memory, there may be an entirely new way of looking at looking at a computer. If the memory and the logic are integrated, maybe this is starting to act more like a human brain. It would certainly be faster than a current computer, but perhaps it's also simply different, more parallel. Perhaps it's not just field programmable, but we could actually arrange for it to train itself, where the currents from one would produce a magnetic field which would flip another one, and so we could start thinking of training and things like, again, getting closer to the way a brain works. So it's at least somewhere out in the very speculative far future the possibility that all of this leads to a very different form of a computer than is currently used. So let me conclude, and I'm going to note below in my conclusions things we're actually working on in purple. So to conclude and to summarize the talk, electrons have spin as well as charge, and the charge, which is negative, is used for transistors and nearly all present electrical devices, including light bulbs. The spin part of it leads to magnetism, and that's used for information storage, but is not used for transistors at all at present. In order to combine them, we have to be clever. Nature provides us with a palette, this periodic table, but sort of like an artist, you have to figure out how to combine them. There's only a limited set of colors in an artist's palette, and we have a limited set of elements we can work with. But nonetheless, we can be quite creative in how we combine them, the structures that we make, not just the which elements we choose, and their structural arrangement. Okay, but it requires exploration. And I do note that most of the great technological advances that came in the last century actually grew out of new materials, out of somebody discovering some new material that wasn't in the periodic table. Adding magnetic moments to silicon strongly affects the current flow, and I showed you this with our amorphous system. And there's some very fundamental science that we can study of the interaction between the electrons and the moments. Can we fabricate a spin transistor? In this case, the spin polarized electrons would carry the current, and we would switch the zeros and ones with a magnetic field. And finally, can we use a spin transistor to make perhaps a better or a faster or more reliable, meaning not volatile, wouldn't turn off when the power went down, computers or personal assistants or things like that? And is this concept of an integrated memory or logic, could it lead to a new type of computer, a completely different vision of the way a computer functioned? Thank you. For the amorphous gadolinium silicate, it is large. It is it depends how big the effect you want is. The 10 to the 5th that I showed was an 8.5 Tesla, which is a laboratory superconducting magnet, but is not certainly completely out of the range of anything on a hard drive. A hard drive, you need more like 30. I'm going to mix units here, but 30 Ørsted, which is a 10 to the minus. An Ørsted is 10 to the minus 4 Tesla, so it's vastly smaller. So the magnetic field mismatch is at least as much of a problem, perhaps more, than the temperature mismatch. So the question is, what limits the temperature of the amorphous gadolinium silicon structure? And that is actually, in my opinion, the $64,000 question in this problem. We don't know. It is clearly, the effects go away in a very continuous way. So the effects are gone, well, I shouldn't say they're gone. They're down to 1% by about 90 Kelvin, which is slightly above nitrogen temperatures. But they're still measurable. There's one obvious limiting factor, which is my ability, or the ability of a magnetic field to align those gadolinium cores. The gadolinium cores have this thermal disorder, and so at higher and higher temperatures, it gets more and more difficult to align them even with the same magnetic field. But the effects go away faster than that. That is not a sufficient explanation. That would explain part of why it goes away with temperature, but only part. There's something much deeper happening as we raise the temperature, and we believe that this is actually, well, it's likely that it's a quantum mechanical effect and not, and that actually is something we'd like to study. We're studying it right now by substituting germanium for silicon, and that has a very profound effect. It shifts it the wrong way if one is interested in practical applications. It shifts everything down in temperature. But a large shift, significant shifts. And so we're hoping by understanding the shift of substituting germanium for silicon, we will understand what limits that temperature. What we'd like to do is go the other way, of course. And so we're going to try and make carbon, amorphous carbon with gadolinium in it, and hope that that pushes it the other way. But the answer is it's a research problem. We don't understand it. Good question. So the question is, if it takes a large field to switch the transistor, to switch part of the transistor, how would I bring a magnet in and switch one without switching all the others? There's a two-part answer to that. One is I hope I didn't mislead people. The gadolinium silicon requires very large fields, but the spin transistor would actually be quite small fields. The difference between the two, in the gadolinium silicon, I'm having to line up individual gadolinium moments, and that takes very high fields. In the spin transistor, I have an entire iron layer, and all I have to do is switch the direction of the iron layer. It's much more like the read head technology that's used in the computers right now. So actually, it would not take very large fields. But your question is still a very good one. How do you, even with a small field, how do you apply it to one and not get crosstalk with the others? And that is something that people are worrying extensively about right now. One of the technologies I didn't mention here, there is substantial research effort into what's called magnetic RAM, which is to turn the RAM part of the memory, the random access part of the memory, into a non-volatile memory, which based on magnetism. And this crosstalk issue is a big deal, is how do you get a magnetic field? It limits the spacing, basically. You have to have them far enough apart that you can apply a magnetic field to one and switch the one you want, but not switch the others. And you get into architecture questions that are really interesting with word lines and crossed bit lines. So you pass current one way and then you pass current the other way, and the only one that switches is the one that has both. So it's a big problem, and they call it the half switching problem. That may be the wrong word, but I think it's called the half select problem. How do you get the one you want to always switch and none of the others to ever switch? So the question was, right, the question is, could I fit some of the rare earths into some of what are called compound semiconductors, which are, instead of sticking to the elemental semiconductors, silicon and germanium, start working with some of the compound semiconductors, which are further down the periodic table. Certainly the small ones you can't. Gallium arsenide is as small as silicon, but some of the larger ones, that's a good question. Nobody's tried. People have focused very much on iron, cobalt, and nickel and tried to put those elements, or manganese, which is another slightly complicated, but another magnetic element up next to iron, cobalt, and nickel. Put those into these compound semiconductors. But it's a good question whether some of the bigger, which people don't work as much on because they tend to like the gallium arsenide and so forth. But that's a good question. Perhaps it could be tried.
Well, if there aren't any other questions, I'd like to thank Dr. Hellman for a very
Thank you.